Good morning. Can you hear me?
Yes, sir.
Yes, doctor.
Okay. I have some construction sound here. Okay. My mouse seems to be insensitive. Right, okay. So we start off with the first class for particles today. So I'll give you some introduction of the subject and what we'll be doing for the whole semester, and then we'll move on to the class today. So I only have 58 of you, but my spectrum shows there's 78 registered, so 30 more is missing. Okay, and our WhatsApp chat shows there's 80 of you. So I don't know which is which. So anyway, there'll be recordings. So those who are not here, they can still follow the recordings. Okay. Right. Okay. It's not request, right? Okay. Right. Because if there's someone who's waiting to be assessed, waiting to be accepted, just let me know. Because for now there's no one, so I'll just proceed to the class. Okay, I've not shared screen yet. So many. Okay, so that's my screen. You can see, you should be able to see my screen now. Okay, so this is our particles technology links. Okay, so it's auto that I've almost updated all the meeting links that we will be meeting. So you as per our week, so you just follow which week that we'll be doing. So this week and next week will be on this link. Okay, and then the following third and fourth week will be on a different link. So usually I do these links because I share some files here and I leave it here. So I happen to leave it here, so I'm planning to just build on it if I need to. Okay, I'll find a way to put in the recording, but I do have my previous recording. This is actually, I used this link last year, so I'm just building on it. So we can still use some informations that are available, and I think my recording of last year is also still available, and most of my slides are actually updated between 2020 and 2021, so I am planning to use the same slides, not much updates. Okay, if there's updates, then I will update it. Okay, so I've also updated this Martin Rhodes is our textbook. Okay, I'll be using this textbook. throughout the course. So in fact, my slides are also from this textbook. Simply because I'll explain to you, and then you can always go back to the textbook to learn more, to understand better, and then the examples also from there. So, and you also have exercise, so you can also do exercise from Martin Rhodes. And if you realize, I also share it in our WhatsApp. Okay, I just share it. Yeah, okay, I just share it. Okay, so you can still use that. I still think second edition is the latest. If anyone find even latest edition, let me know. We can all use the same one. Okay, and then I've also updated our e-learning planner. What I'm planning to do this semester. So it's here as well as it's also in the where is it? It's also in the spectrum. It's also in the spectrum. Okay, so I will take you through it. So as I go through my slides, there will be a section for the planners. So I'll take you through it. So let me share the slides first. Okay, all right. So this will officially be our first class. I'll do some course introductions. So in this particles technology class, what you are expected to learn is you should know how to characterize particulate solids. Any solids that are in particles form. Okay, and then you should be able to apply suitable equations for different particulate systems. Okay, so you can have colloids, you can have particles behaving like fluids, you can have particles moving in a pneumatic system. So you should be able to use different equations to calculate the particle system. And finally, you're expected to design some unit operations involving particulate systems. So we will, in this course, we will be learning some design of unit operations. We'll be learning some unit operations like packed bed reactor, fluidization, fluidized bed reactor, and then we have cyclone, we have hopper, we have pneumatic design, and we also have mixing of particles. Okay, so you will learn how you can design simple designing principles and parameters for these unit operations. Okay, so these are what you are expected to learn. So this is the course outline. Okay, so we will do, first 2 weeks we'll do on particle size and distributions and how you differentiate different particles, how you measure different particles in order to achieve our first learning outcome, the first course learning outcome. And then you'll be introduced to different particles related systems like packed bed, filtration, fluidization, pneumatic, cyclone, hopper, and mixing. So you learn these different systems. In these systems, you will cover both ClO2 and ClO3. You will learn how the system works, how you calculate the equations in the system, and you will also learn how to design that unit itself. Okay, so we will learn both in this. And last but not least, we have this health, fire, and explosion hazard. So we also learn the safety bit, because I think it's always very important to have some safety factor of this of whatever we learn, because we are chemical engineers and we are always fed with the word sustainability, and we can't run away from safety, health, and environment. So I incorporated this into this topic in order for us to know what are the hazards that can be that can happen due to particles. Okay, so that covers ClO1, which is again characterization of particulate solid. So the solid can also be hazardous. Okay, there can be certain time weighted average values where you can inhale things and then it can affect you. So there can be a lot of safety drawbacks when a particles are actually left uncontrolled. Okay. Right. So the reference book, so as I just mentioned, so this is Introduction to Particle Rules. So the latest I found so far is this book. So if there's any latest, please do let me know. So you have it both in the WhatsApp, like I just mentioned, and you also have it in this our spectrum. Okay, and then back to the course outline. Okay, this course outline, which I have told you I shared in this form. So I have pretty much outlined what our course is going to look like. Okay, so first week we will be, although I started this week, so don't worry, I will still be covering this part. Usually what happens is that in this first 1 hour class, okay, most of my 1 hour class, I will discuss the assignment that I give in the 2 hours class. So 2 hours class is my most important. So the 2 hours class, we have lecture as well as I give you the assignment on Wednesday. On Mondays, we will discuss the assignments. And then your submission will be on the following Wednesday. So that's how it is going to work for the whole semester. So I have outlined it. So how well we follow the plan, it all depends on how things changes around us. Okay. So I have put in the topics that we will go through and also the assignments. Most of the assignments are pretty much the same as what I have done last year because it was all updated. So I will still update it from regularly in accordance to our class. So maybe for the I will update for the first 2 weeks and then I will do it every week. Okay, if I can do it, if I can find time to do it for all, I'll try, but I can't promise that. But the slides are already there, okay, for the whole semester. So this is our schedule. So I've also incorporated our holidays and semester breaks, and then we also have 2 Mondays off, so it doesn't affect us much. So I plan it accordingly. So you notice our test is on the 9th week. Okay, that's the plan. So that's like 2 weeks after the semester break. I'm planning for a test, most likely online. And then feel free to ask me questions. You can type on the chat box or you can interrupt me. At least I feel that I'm not the only one just speaking to the wall. Okay, and then I have just incorporated things. So usually my course is designed for 12 weeks because usually we have at least 2 weeks off. But this week, this time, we have uninterrupted, the 2 hours class is uninterrupted. So we have 14 weeks of lectures. So I might add in some new bit into week 13 and 14 because usually I rush to complete my syllabus because there's always holidays. But this time, since there's no holidays, so I might add in some interesting activities towards the end. Okay, but mostly week 14 is a break because it's a revision, and that's it. And usually my final exams, there are 4 to 5 questions since you have taken my kill, so it's roughly about that. So I also allow a cheat sheet where you can copy questions, and it's usually for 2 hours. Okay, so this is the planned outline and you can access to it. So our assessment is 40% continuous, 60% final. So this is common. So usually last time I used to conduct 2 tests. Until about 2018, I used to conduct 2 tests. But after the pandemic and all, I just don't want to stress the students, which is actually why I have this course revision. Usually it's my test period. Okay. And sometimes I struggle to conduct also if there's leave. So that's why I've reduced on the test just to reduce your stress. I don't want to stress you up. So it's going to be 1 test. So most likely usually it's between 10 to 15%. Okay, and then the class activities will be accordingly 25% to 30%. So if I have less submissions, if students are purposely playing around, not trying to submit and all, then I will increase the percentage of the activities. So this one depends, so I will decide, but it's usually between, this is 10 to 15, this is 25 to 30. Okay, so if you look into this form assignment of mine, I have roughly placed the percentage that you get for each of your assignments. Okay, again, this is my plan, so it may not be exactly this, so I might change, I might add. So when I add, then I will let you know. When I add or I change a little bit, I'll let you know. So since you see, I mean, it's 2%, 1%, so the assignment is also accordingly, just like our statistic class. So I give you a few questions for you to answer. Then I give you with the answer, then you have to do it. So that kind of activity, so I can't give you 10 or 15% for each assignment. So although it looks a lot, it's actually a cumulative of like maybe 3 questions, 4 questions, one long question where answer is given and you're expected to do the assignment. So that kind of activities, okay, not to worry. And then I used to practice this as well. I purposely put it in here because I want to show that we are trying to support you, but you don't take advantage of it. Okay, I used to penalize students for submitting late, especially after a week. I don't accept their submission. And again, due to pandemic, I have loosened up on this. Again, I don't want to stress students up. I want your learning to be more relaxing and pleasant. So I've removed this, but still, like I have to give your continuous assessment results by week 14. Okay, so on week 13, because our classes are Monday and Wednesday, so on week 13, or I will actually collect all these results, and I will tabulate your marks for continuous assessment. So even if you miss out some of the submission, at least make sure you submit by week 13. That's my requirement. I will have the due dates, and it's good for students who beat it on time. But if you happen to not able to do it, but make sure you at least submit it by week 13. By the time I mark the assignments and calculate your marks. So if there's so many of you, if you expect me to go back and do it just for one person, honestly, it's troublesome. So be a little compassionate to me as well as a lecturer. It's not just me trying to accommodate you. I think you should also have some sort of compassion for your lecturers, because this online learning is also burdensome for us. A lot more things to do and prepare for us, to be honest. We are equally stressed. Okay? Right. I think that's all that I wanted to inform you. So, because I'm going to start the class, so this is already starting the lecture already. Okay, I want to introduce the spectrum bit, right? So your attendance is here. Okay, so I updated it. I'm not sure why it looks so different. Okay, wait now. Okay, I created this link. It was different then, so I don't know why it's different now. Okay, you're expected to sign in your attendance here every week. Okay, let me just see what happens. I don't know. I have to give. Oh, they changed something. I have to be present as well. Oh, I know why. I'm a student here. Okay, I purposely put myself as a student here. That's why I cannot see whole attendance. I'll show you in a while. But the reason I put myself as a student here is I want to show you that I've got all the slides in place. Okay, but it's just that I didn't put the year so that you don't, because you may not be sure. So if you notice, there's assignment 1 here for single bulk, but I didn't put the assignment here because last year I didn't have time to do this. So in your e-learning, your packed bit is actually assignment 4. Packed bit is assignment 4. So I have 2 and 3 assignment. I have it. I have it there. It's just that it's not in your view. So I will update that part. Okay. So what is need to be done for today? It's updated. Okay. Okay, this is my first time viewing in students' view, so I've updated, so it's due for submission next week. Okay, so I'll show you about the attendance. I just have to return to my normal role, and now I can see the attendance, and this is your attendance for this week. Okay, so some of you have done it, some of you haven't, so this is how it is. Okay, please do it. So there's 65 who has signed in, but the meeting has 67, so one more person hasn't put your attendance in, and this is how it looks. So you do this for every class. So I have already done this for every class until the 14th week. Okay, right. That's all. So I will have announcements here. This course forms gives you details of what we'll be learning for this semester. So you can just look around. Okay, so for now, this is update. So from my view, you can see I have assignment 2 and 3. It's there. So I will update it when you have to do it. This is next week's work. So this is for this week. So I will update things as we go on. But I think my slides are pretty much finalized. Okay. And some of my lectures may also be on YouTube, because I managed to put some of my lectures in YouTube. Not just extract my lecture and put it in YouTube. I prepared my scripts, and I actually recorded the lecture for the students. So this is a recorded lecture with scripts, with me recording it for students. Okay, I had to do this for some students who may not have good Wi-Fi access previously. Okay, now I think a lot has improved. Okay, so I have some lectures which are on YouTube in my channel. So I will direct you to my channel whenever I have to. Okay, so this is my channel, so you can, or not promoting, you can subscribe if you want, but I have few subjects here. So I also have our own subjects which I have recorded. Okay, so my hopper design is a popular one. I always get compliments for that. Okay, so I also have other subjects here, so don't get confused, but I'll give you the links whenever you need to. So some of these subjects will be asynchronous, where you will be watching video. Okay, I think pretty much explained how things are going to be. Okay, any questions? Any questions?
No, doctor.
No? Okay, good.
No, doctor.
Okay, it should be clear because my style is, I think, the same like our statistics. It's the same style. It's easier to follow just that. Okay, so we're going to start the class. Okay, introductions to particles. So what is a particle? Okay, your particles comes in different forms. Okay, so the most general that you have already been exposed to is solid, liquid, and gas. Okay, there's also in betweens like amorphous. Okay, and liquid and gas can be fluidization. Okay, actually fluidization, solid and liquid. All right, but the main is solid, liquid, and gas. Okay, so what is a particle is actually also an evaluation of a system. Okay, so when we touch it, when we evaluate the system, it can mean different sizes. It can mean different characteristics. That it can be something long, it can be something something organized, something cube, it can be something cylindrical, so it can be something soft and long, or something, this is also soft. And then, so it is an evaluation of a system. It is how one evaluates that particle, because we cannot exactly say this is particle. So it is a bunch of something, or it is a representation of something. We equate it to something. Okay, that's how we see the world of particle. Okay. So particle is something that remains suspended for a period of observable or measurable time, not dependent on its size. Okay, if it is not observable or measurable, then we won't be able to measure it. So we won't know what that particle is. So it has to remain suspended. And it's a part of a whole. So particles is not on its own. It's a part of the whole thing. Okay? And minute individual entities. Okay, it's a minute entity, and it's apparently stable with at least moderate cohesive forces. Cohesive forces means something that can flow. Okay, so it has forces, but it flows. But it doesn't flow alone. It flows with a group of particles, bounded by the optical or other means used to identify it. Okay, so these are general explanation about particle. There could be more, there could be others, but this is what I want to expose you to. This is the idea I want to expose you to. So why particle technology is important? So particle size influences many properties of particles material and is valuable indicator of quality and performance. Okay, so we don't want, when we use something or when we do something, we don't want it to be rough. But there are some parts that we want it to be rough, like your roads. We want your roads to be not very rough, at the same time not smooth. But it should not be bumpy. Okay, and then for your tire, we want the tire to have that corrugation so that it ensures stability. But at the same time, it should be able to be handled. So it should not be hurting you with its roughness. You don't want to have a lump or bumpy air pocket in the tire. So that will affect performance. Okay, so this is the importance of particles. Mainly, its quality and also performance. So there are different forms of particles. We have powders. Okay, these are particles, but I can't show you this is particle. Okay, this is a lump of particle. Okay, so when you have a powder, you don't want the powder, when you actually get the powder out, shake the powder out, you want it to flow. You want it to be smooth when you use it. What happens when it's lumped inside? When you try to put your powder out, you don't get anything out, or you get very little dust out. That affects the performance of the powder. And then you have powders. Okay, we call this loose powder. Okay, so the whole intention of loose powder is we want the particles, each small little particles, to be separated and covering the face evenly. Okay, that's why we use loose powders. If you notice the loose powders, right, they'll touch very little of it and then they'll dust it off and then they'll put it on the face. So the whole idea is it should be even and well spread out. So that's it's important that the powders can be loose, can be spread out, and can be covering the face. Okay, it cannot lump. And then, so powders is one form of particles. Okay, it's not a type of particle; it's a form. How particles can be present in our life. Okay, so you have powders, you have suspensions. Okay. So a suspension is a heterogeneous mixture in which particles settle. So you have water, you put in a sand, some will settle, some will be floating. Okay, so the mixture still has undissolved solid particles settled at the bottom with some particles still floating. Okay, so this is another form of how a particle can be present. This suspension itself can have different form of how the particles are present. So it can be a stable suspension, then it can be unstable suspension. These are all unstable suspensions. Okay, this is early stage suspension. That means some are singly floating around, and some are actually being adhesive to other particles. And then these are late stage, where there are more particles lumping together. and then eventually it can also be a sedimentation where it sediments out. It's not a stable suspension. Okay, so these are forms of particles. Then we can have emulsion. Okay, emulsion is a dispersion of one liquid in a second immiscible liquid. So dispersed phase and continuous phase. So in emulsion, we have a phase where it's dispersed, another phase where it is continuous. So that means it's sort of dissolved. So the different types of emulsion is either hydrophobic or hydrophilic. So like you can have oil in water and water in oil, so they cannot be together. But so they will have this hydrophobic and hydrophilic characteristics. Okay. And emulsion stabilization. Okay, so these emulsions can be stabilized with some emulsifiers. Okay. So this explains some of these instabilities, just like our sedimentation just now. So our emulsions, if you notice, if you put oil into coffee, let's say, people drink coconut oil in coffee. So if you put coconut oil into your black coffee, you will see creaming. Okay, just give me a minute. Okay, all right, that was my mother. So family call, must pick up. Right. So this mechanism of emulsion instability, so you can have different instabilities, just like our suspension instabilities. Suspension can be stable as well as unstable. Then we also have emulsions. So emulsions can have creaming. Emulsions can also have sedimentation. So when we put coconut oil into a black coffee, you will see all the oil are floating on top. It doesn't really mix or get into the coffee. Okay. You can also have cases where it sediments. Okay. And we can have flocculations where it is still floating around in small sizes. Actually, the same oil, right, at some point, okay, you will see there can be some flocculations. There can also be some coalescence. It's not like just creaming on top, but it's big circle formed in the water or in the coffee. You can see that as well. Okay, or it can just be aligned, like completely not miscible. It can be in the coffee, in the liquid, or it can be completely not miscible like this. Okay, so these are all examples of emulsions. And then it can also be present in the form of aerosol. So aerosol is very related to the millennium generation, because nowadays we have started measuring PM 10, PM 2.5, PM 1. PM means particulate matter. In fact, we are moving towards PM 0.1. It means we have that very, very small particles that are floating around in the air that affects our health. Okay, and one of the reasons is aerosol. Okay, so aerosols are the sprays that you use. Okay, so they give you very small mist, dependent on the kind of pressure and kind of liquid that we use. So we use a lot of aerosols, all these nanotechnologies, even foundations which uses nanotechnologies where you spray. Okay, so these are all aerosol particles. So there are so many different types of aerosol particles nowadays, which not only of course you use it and then it gives you the product, but it also is left in the air and floating somewhere, okay, because of the size, because of the lightness. So those are different types that I have identified. We can find more. Evolving particles, this particles technology subject keeps evolving. Things becomes new. We get a lot because it's an area that keeps evolving. Okay. Why is particle technology important? Okay. Usually I throw this question to students because I wanted to speak up. So define industries for which particles technology is important. And then you can also share your personal experience related to it. So can I have a few of you speaking up on this? Huh? Can I have a few of you speaking up on this? Otherwise, I have to call your names. How particles technology affects you? Amira Afina. Are you there, Amira Afina? Amira Afina? So you switched on and you left. Aina Shakira?
Yes, doctor.
Aina, is it?
Yes.
Hi, Aina. So can you share with me the answer to my question just now? Okay, why this thing is closed? On what are the industries where particle technology is important, and share your experience if you have any personal experience. Can you answer, Aina? You can answer on chat box also. What are the industries particles technology is important? Share personal experience if you have. Yes.
For the pharmaceutical.
Okay. Why? Why it's important in pharmaceutical? Why it's important in pharmaceutical?
To produce a medicine.
Okay, so what happens? What can go wrong with the medicine? Why particles is important? Okay, now I ask another person. YamZK.
Yes, doctor, can you hear me?
Yes, I can. So why do you think particles technology is important in pharmaceutical industry?
I think particle technology is important in many industry, especially for industry that producing powder because it studies the properties of fine solids. So not only in pharmaceutical industry is important.
Okay, this is a very general answer. So my question is, why do you think particles technology is important in pharmaceutical industry? Why? In which area? How it's important? What could go wrong?
I think maybe in separation when it deals with the fine particles. If the separation goes wrong, it might be, let's say, it should be pure component A with purity of maybe 99%. But if it goes wrong, maybe it doesn't reach the desired purity,
Okay.
and it is harmful for the medicine.
Okay, good. All right, so this can be a reason. Okay, so you want all medicines. Thank you, ZK. All medicines comes in a mixture. Okay, you have active ingredients. The active ingredients are the medicine, and then you also have fillers that carries the active ingredient. So when we mix them, it should be in, like, every time I take a tablet, I must be confident that there is 20% of ingredient A, 20% of ingredient B, and 60% of the filler. Okay, and then it also has confidence interval limit, the one that we learn in statistics. So I am confident there's 20% by 95% confidence interval. So the particles mixing should be proper in order to ensure that every tablet carries the same, similar amount of active ingredient and filler. Okay, that's one. There's another reason is, like, I worked in a pharmaceutical industry, and I did quality control. Okay, so one of the tests that I conduct is to see the layering of your tablets. Okay, so your tablets comes in different colors. You have red, blue, yellow, and so on. Okay, so the layering or the covering of the tablets must be just right, so that after you eat the tablet, after about certain period of time, let's say half an hour, it should, the top cover should start depleting, diluting into you, and the active ingredient should be released. If I put the layer too thick, if let's say I have that batch, the layering is thick, maybe I have 2 or 3 layers or very thick. So let's say instead of half an hour, it is taking 2 hours to just break down. Then it affects the efficiency of the medicine on the person who eats it. So we will reject that batch. Okay, so that's another example how important particles technology is in pharmaceutical industry. Okay, so can I have maybe another 3 more industries? Can somebody answer? Show up. Yeah, Maria.
Yes, doctor.
Any industry that can think of?
I had pharmaceutical in mind, but it has already been said by CK.
There's so many others.
Trying to relate, doctor.
Just any that has particles. Everything that you use is particles. Everything. So just give me an industry.
Probably in manufacturing.
Manufacturing what?
Manufacturing.
Manufacturing.
For instance, like aerosol, like
What
mosquito spray.
Huh?
So like mosquito sprays.
Okay, so mosquito sprays. Name one
Yeah.
mosquito spray.
The Shaltox, yeah.
Okay, good. Shaltox. Okay. So what could go wrong if the particles, some particles side of it is affected? What can go wrong?
It can be the level of the aerosol that is being released from the per spray that might affect the percentage, and also the quality of the aerosol.
Good. See, now you're starting to think. Okay, thank you. So when your aerosol, you're also expecting certain percentage of active ingredients and carriers to be present. So if the mixing or if the particles are not properly present, then it will become ineffective. So it affects the quality. Okay, so the aerosol should also be present, continuously be present in a fluid form, where when you press it, you must get the aerosol. So if the fluid form, let's say it happened to sediment, where the active ingredients are down, and then on top you only have other liquids, so when you press, you get only the liquid. Or if let's say it start to lump up, when you press, you won't get anything out. It becomes difficult, it becomes tough for you to press. Okay, so can I have more? Any volunteers who wants to say? Muhammad Hadi Fikri.
Yes, Doctor.
Hi Muhammad.
Yeah, hi, Doctor.
Banyak Muhammad. Hi Hadi. So Hadi,
Yes,
you have
yes.
any experience?
I think particle technology is important in order to reduce the size of the particle and also for the particle separation, such as the sieving, magnetic separation, electrostatic
No, wait.
precipitation.
Sorry, what is the industry?
I think it involved in a lot of industry, just like they mentioned just now, like aerosol and also the pharmaceutical, and it also can be involved in the petrochemical, agricultural technology, just like the fertilizer, Doctor.
Okay, I want specific. So you said agriculture, you
Yes.
said fertilizer.
Oh, yes.
Okay, so what can happen to fertilizer? What can go wrong with the fertilizer?
So for the fertilizer, I think the particle size have to it involve the particle sizing, and also whenever the fertilizer dissolve, or the porosity of the fertilizer, in order for it to be easily dissolved in the soil.
Okay, so for the fertilizers, to act accordingly. That means you're expecting it to release certain contents, again also active ingredients. Then it should be able to move out freely and not just stay in lumps or clump up for hours, and then it's not being effective on the plants. Okay, so that fertilizer, so agriculture fertilizer, that's good. Can I have two more? Two more industries. That means you give me different industry. Safayet Aziz. Are you there? Safayet? Safayet Aziz, are you there? Okay, so some of you just switch on my lecture and then you're gone. Or you don't have mic. If you don't have mic, you can still chat. It's not acceptable. Nurina Bey?
Yes, Doctor.
Hi, Nurina.
I think cosmetic production.
Good. So can you give me name specific cosmetic?
Name.
Any specific, any product, cosmetic is a big range, right? Any particular cosmetic can you name?
Sunblock.
Huh?
Sunblock.
Sunblock. Okay, good. So what can go wrong with particles in sunblock?
Actually, there's technology that use nanoparticle. So when the size of the particle is small, so it will be easier for it to to cover our skin.
Okay, good. Okay. So if your SPF is lumped up and all, and then when you put on your skin, it's not gliding through, then you will not like the SPF. Okay. And SPF is oily, so chances are very high the oil can be separated. So once the oil gets separated, so the whole thing becomes oily and the absorptions becomes difficult. Okay, so these are the problems that we can have. Okay, so I've got 4 industries. I got one last one. Daniel Balin, can you give me one industry that has not been mentioned by your friends? Daniel Balin. Okay, I'm going to find a way.
Hi, Doctor.
Hi, Balin. Hi, Daniel.
Hey, I have not been in the industry, but I think one of it is something to do with the separation of particles and powders because I was in PBL with you last semester.
Yes. Okay, good. So, which industry?
Maybe something related to like something to do with powders. I'm not sure actually, but
Huh?
wait.
Any industry. Any industry. Every industry requires particles.
Maybe the food industry.
Food industry. Okay, good. So, which food can be affected? Just give me one particular food. Then explain what can go wrong.
Maybe like powders like cocoa powders or Milo or something like that. Like it.
Okay. So
Yes.
let's pick up Milo. Every semester, someone will pick up on Milo. So what can go wrong with Milo?
Maybe something related to the size when separating the powders or the process. Maybe like cocoa powder, it affects the bitterness, something like that. It affects the taste, the quality.
Yes, the texture.
Yeah, the
Right?
texture.
When you scoop your Milo is actually a mixture of the cocoa powder and something else and the sugar and so on. So it's also coated. So when you scoop your Milo, so every day sometimes you just fix 2 spoons of Milo, 2 spoons of milk should give me my best Milo. So every time you do that, you actually get the same consistency. You can only get the same consistency if your particles are well packed in that Milo bag. Okay, so if particles system goes wrong in that Milo pack, you will not get that consistency. Okay, everything that is around you involves particles and requires the particle system to be in order for you to get the quality and performance. Okay, so there's so many industries which some you have covered as well. Okay, so all this requires particles technology to be in to must be checked. It must be in a good desired quality in order to deliver the performance. Okay, so particles affects us in many ways. So just now when I asked you the question, I've also asked you how it affects us. So we are done with this part. Okay, right. Let me just see how many slides I have. I'll decide whether we should go for it. Just finish it. To finish. Okay, we take 5 minutes break. Okay, just a quick 5 minutes break. And then we resume. So my clock is 12:03. Okay, maybe 7 minutes. So 12:10 I resume. So I only have a few slides to go through, and then I want to we will discuss on some work examples before I give you the assignment. Okay, so I will probably need another half an hour to finish the class. So I see you all at 12:10. Right, we'll resume. How particles affects us. So in appearance, okay, so a lot of our applications, now we are into aesthetics. We want to look beautiful, we want it to be glossy. It can be your nail polish, it can be lipstick, it can be paint, it can even be cabinets. So we like things to be glossy and attractive. So that is that is because of the particles. And then cocoa, so like how we mentioned just now, so we don't want cocoa to lump up. So when we do our cookies, when we do our bakings, or when we have our Ferrero Rocher, so we want the chocolate to be smooth, okay, and flavorful. Then reflectivity, so if you know the roads that we have, the yellow lines, sometimes at night it lights up. Okay, it's actually beads of particles, glass particles, which are layered evenly. So when it should be even. So when cars passes by, it's not rough, and when people walk, it doesn't slip people. And at the same time, it should be able to reflect even colors. See, it's not like one darker or one lighter. They're most of the time even colors. Okay, so it gives you a good reflectivity. And then cement, when you build structures, when you even them, so you want it to be soft, you want it to be smooth. Okay, when you mix them, it should mix well. And then in dyes, we want colorants. When we use it, we want it to give us the color that it is promised. And then it should have a consistent particle size in order to give the spreadability. Okay. And then we can, in pharmaceuticals, like how we just we discussed, so it can be different particles that is required in the tablet. So we want it to be mixed properly, okay, formed into table, and then it should be the covered layer should be just the thickness that we require for it to be. Once it's in our bloodstream, it should dilute at the required time. So the thickness should be fixed. Okay. In cosmetics, when you apply it on your skin, you want it to be smooth. You don't want, some of it is promised non-moisture absorbent, so it should also not absorb the moisture. Okay. So if there's dust, if it is glittery, so it should give you the glittery well spread out, not just when you put all over the face, then you only get it on one part. There's glitters and other parts it's not. So usually you don't get like that. Okay. And your lipsticks, you want it to be smooth. So when you glide it through, so it's smooth and even. It gives you the color just right. Okay. So these are some of the industries which I have listed, and most of it which you have already mentioned when I asked you. Okay. Of course, there's so many more. Almost everything we use, there's particles involved in it in different forms. Okay. So these particles, how do we measure them? Okay, the measurement of a particle is dependent on the product or the outcome. It depends on what the particle is. Okay, so we only measure what is required, and we only use that, what is necessary. We don't have to include everything of a particle to define the measurement of the particle. So I'll come to that. I'll tell you what I exactly mean. So most of the time we have well-defined particle size, okay, which is this. Okay. These are well-defined particle size. So you have a hemisphere, you have a sphere, you have a cuboid, cube, and then you have a cone, then you have a pyramid, trapezium, you have a cylinder. So all these have formulas. Okay, and you have mathematical formulas, so you can define the diameter or the size, the volume or the surface area of these particles. But it's very unfortunate that in real life, most of the particles does not follow exactly accurately to these sizes. Okay, you have many different size. A same particle can have different shapes. Okay, you can have a shape of a butterfly, flowers in different shapes. So this is what we can have. Okay, things can be in many different shapes. So we have to find a way where we can give a general sizing that can be used worldwide. Can be used. If let's say I want to talk to you about spaghetti strips, I should be able to tell you if I'm talking about 10 pieces of spaghetti strips and it's like 30 cm long, as long as my 30 cm ruler. So you should be able to imagine the same thing. Okay, so I have to find a way how you can you have to find a way how you can define the particle size measurement that can be understood by the other person. So this is mainly for trading. Okay. So if I have a particle size and I look into the projection, so for a sphere, it is a straight cut, it's a diameter. So you can define a sphere by its diameter. So if I say it is 30 cm diameter, so you can imagine, okay, this is the ruler, this is the 30 cm, and then it's round. So that is the diameter. So you could imagine, wherever I go, I say the diameter is this much, you can imagine a sphere. So if I have a really uneven shape, okay, if I do a projection, how do I define? So I can probably define, okay, the length, whichever one can be, this is the height. So this can be the length. So the length is this much. The height is this much. So when I say that, so you can roughly imagine. So your imagination is also to a cube, to a cuboid. Roughly, you can imagine what its shape is. Okay. So in order to standardize things, we have some ways of measuring our particles. Okay. So describing the particles of a single, describing the size of a single particle, some terminology has been used. So you can use equivalent circle diameter, you can use Martin's diameter, Faraday's diameter, or shear diameter. Okay. So let's see, each of this is listed here. So if I have a particle that doesn't have an exact shape, I can make it into equivalent circle diameter. Okay, so I can try to fit it into a circle, and then I use the diameter and I give you, okay, it's, you know, the size is about equivalent to a 30 cm diameter of a sphere. Then you can imagine, okay, it's going to be about this much and a little bit here and there. So rough, you have an idea what is the size like. So that's equivalent circle diameter. You can also have Martin's diameter, which is you can take the line bisecting projected area. Okay, so you project this, okay, you project, and then you get the middle line. So that is your Martin's diameter. You can also do Faraday's diameter, where you fit it into two lines, and then you take, you have the parallel tangents, and then you take a line. Or we can do shear diameter, where we put the particles side by side, and then we take two same edges and define the diameter. So these are ways we can explain diameter. Explain a particle size. Okay. So because this shape like sphere, cube, cylinder, cuboid, and cone has got a specific dimension and is easily imaginable, so we tend to follow this sphere. Okay, so if I have an actual particle which is a cuboid, okay, I will equate it to sphere diameter. So I will equate it to surface diameter. That means I take the total surface of this particle. I can calculate this, right? So I'll take this and then I'll equate it to a sphere. Then I'll find for the same surface area of a particle, of a sphere, what the diameter could be. So I'll equate it to a surface. And then I could also take volume of this particle and then I equate it to a sphere volume diameter. Or I can also take surface to volume ratio diameter. Okay, so in many cases, we opt for surface to volume diameter for a more accurate description of a particle. Okay, so I'll show you how this is done. So this will be your first exposure to how we characterize a particle. Okay, so first calculate the equivalent volume sphere diameter xv. Why xv? X is the diameter, v is the volume. And surface volume equivalent sphere diameter xsv, surface to volume, of a cuboid particle with a side length of 1, 2, and 4. Okay, so this one, you have a cuboid, so it can be any. So let's say I try to draw, so I can have a 4 mm, 2 mm, and 1 mm. So it is probably like that. Okay, this is probably what you have. So it's 4, 1, 2. Okay, so for you to calculate the volume for a cuboid is easy. 4 times 2 times 1. Okay, so you get 8 mm. The surface area of the particle. So this is volume. Surface area, that means you calculate each surface area. So 1 times 2, and then you have 2 of this. And then 1 plus 2 plus 1, blah, blah, blah. Okay, I wonder why they make it so difficult. Okay, so surface area, how do you calculate your surface area? You have 1 times 4, you have 2 of it. 1 times 2, you have 2 of it. And 4 times 1, you have another 2 of it. Okay, then you get your surface area. Okay, then you are to calculate the volume of sphere. So this is the formula for sphere volume. So you know the volume of the cuboid is 8. So we equate this. If the volume of the sphere is 8, okay, what would be the resulting xv? Then you get your 2.4811. So for this cube, for this cuboid, if it is present in the form of sphere, so the equivalent volume sphere diameter of that cuboid particle will be 2.481 mm. Okay, so we have just equated this cuboid into a sphere volume. The next question is they want to know surface volume equation. So you have the surface area, you have the volume. So it's surface volume. So surface over volume, 28 over 8. So this is what you're looking for. So the surface to volume ratio of a sphere diameter is therefore 6 over xsv. So any idea how we got this? Any idea how we got 6 over xsv? Anyone? Angeline Ong.
Yes.
Any idea how we got this formula?
It is the volume of the sphere of diameter over the equivalent volume sphere diameter.
Okay. So you said it's the volume over the volume.
Yeah, doctor, maybe. I'm not very sure.
Yeah, it's wrong. It's wrong, okay? Anyone else? Mohan Raj. Mohan Raj.
Yes, doctor.
How do we get this formula?
I think similarly to how we did it for the cuboid, we took the surface and divided by volume, right? And we know for a sphere, with the same thing. So I think the sphere surface equation divided by the volume of the sphere's equation, and you'll get 6 over xsv, maybe.
Yes, correct. Okay, that's what you do. you get your surface. This is the formula for volume. So you get the surface of the sphere equation, then surface divided by the volume. So if you put the formula, then you will get 6 over XSV. Okay, right, because this has always been a question, so you can try it yourself. You find the surface sphere surface formula, and then you have this is the volume formula. When you find the ratio, you find this formula. Then you can stick to this formula. So if this is the formula for the volume ratio, and this is equals to 3.5. Okay, as above, as here. So hence the diameter of the sphere, so you can solve for XSV, which is this. So the surface volume equivalent sphere diameter is 1.714. Okay, so that's how we solve it. Then we have worked example 1.6, which uses a different cuboid, different size, asking you the same question. The volume diameter, the diameter of sphere having, so you look for the volume, then you'll also be looking for the surface diameter, and then surface volume diameter. Okay, I'll come to the D and E in a while. So this is the volume of the sphere, this is the volume of the particle, so this is the formula. So when you equate it, you can find the XV. Okay, you find the XV. Then for surface, this is the formula for the surface. Okay, so this is how you find the surface area for the particle. Then you are able to find the surface diameter. And then you have a ratio for the particle, and then you use the formula for surface to volume ratio, and you get your XSV. Okay, that's A, B, C, D. And then we have one more question. So these two are new. So you have one, you are to find the sieve diameter. Okay, so if the width of the minimum aperture through which the particle will pass. So I have, this is my particle size. I want to know which sieve diameter should I propose for this particle size. Okay, so if let's say I have that particle, okay, so this is 1, this is 3, this is 5. So when I go through sieve, right, the sieve will shake. If you have gone through your second year lab, the sieve will be shaken mechanically. You put your particles here, the sieve will be shake mechanically. Okay, shake. So this cuboid will fall on different surfaces. It will fall on the 5 by 3 surface. It can fall on 3 by 1 surface. It can also fall on 5 by 3 surface, 5 by 1 surface. Okay, so it can fall on any shape. If I select 1, I have to wait until the particles fall on that one surface in order for me to let it pass through. Okay, which is quite impossible too, because that's not the most stable position. Okay, the most stable position can be 5, but if I put 5, other particles bigger than this can also pass through. So 3 is the best option. So when it's on the 3 by 1 or 5 by 3 position, there's chances for it to flow through. So looking at this example, your sieve diameter, the rule of thumb is always the second smallest dimension. So this is the smallest, this is the second smallest. So always the second smallest dimension will be your aperture. The smallest square aperture through which this particle will pass is 3 mm. Hence the sieve diameter should be 3 mm. So we're looking at 1 by 3. Okay, and then projected area. The next question is the projected area diameters. The diameter of a circle having the same area as the projected area of a particle resting in a stable position. Okay, if you look back at this, so let's draw it here. So if I look back at this, so the most stable position is this one because this is 5. So we have what are the sizes? 5, 1, and 3. Okay, it is the most stable. So projected area is what you see from this side, what you see from here, and there's 3. Okay, this one is at the bottom and this one is at the side. Okay, what you see. So you either see this, you either see this, or you will see this. Okay, this and this the same. This top and the bottom the same. Okay. Yeah, and this side and the other side is the same. So these are the 3 projections that you can see. So the first projected area is 3 mm, 1 times 3. Second projected area is 1 times 5. And the third projected area is 5 times 3, 15 mm. Then you know area of a circle, this is the formula. Then you just equate it to this area of the cuboid. Then you get your projected area diameter. So in this case, you will have 3 because there is 3 projected areas. So different shape will have different projected areas. If the projected areas are the same, then you just do 1 because either it falls on this side or that side, the projection is the same. So these are your projected area diameters. Okay, so this is the first step of particles characterization that you have been introduced to. This is the same question. Okay, this is the same question. So last time I used to just give this and then I get the students to do and then I'll explain. So now I've put it in here. Right, so you can try it on your own if you want. And I will do particle size distribution and bulk sizing in the next class, next week, Wednesday. But I have assignment for you here. Okay, so for this class, you're expected to do this exercise 1 and 2 and 3. So I have 3 exercises for you with answers. Okay, attempt it and make submission to the portal. Okay, so we will discuss how these questions are done on Monday. Okay, on Monday we'll discuss this answers. And if we have time, I'll probably give you some extra questions. So on the Monday class is more like a tutorial class. Okay, that's all for today. Any more class? Any more question? Not anymore. Any question? I have not got any questions from you. No? Clear? Okay, so your portal is also ready for submission. So see, I have 78 of you registered, but I only have 66 of you in class, so 12 missing, 12 not here. Okay, so if you don't have any questions, the recording will be available for you in this link. Next week, I'll see you on Monday at 10 o'clock in the same link that we are in today, because this link is for 2 days, 2 weeks. Yeah, okay, so next week we'll be on the same link. So I'll see you tomorrow, next week at 10 on Monday. Thank you all.
Thank you, Doctor.
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 Thank you,
Thank you,
Doctor.
Doctor.
Thank you, Doctor.
Doctor.
Thank you, Doctor.
Thank you, Doctor.
Dr. Jega. Dr. Jega, you are muted. Dr. Jega, I have a question.
Yeah.
Okay, so I couldn't hear you clearly just now. So just want to make sure that for assignment 1, we need to submit exercise 1.1, 1.2, and 1.3, is it?
Yes.
Okay, thank you.
Okay.